Hi guys, it's your science teacher here, back with another video. This time I'm going to go through the first unit of the chemistry AQA syllabus, which is atomic structure and the periodic table. So without further ado, let's get started with today's video. Because this unit is the first unit that you will cover, this goes through a lot of the key principles of chemistry, and without understanding this topic really well, it's really hard to understand a lot of the rest of the course. So let's start off with the first chemistry principle, which is that everything is made out of atoms. And how we define an atom is it is the building blocks of all matter. If I show you this box here, this is showing just one atom on its own, and an atom is comprised of a nucleus at the center, and it has electrons orbiting around it. This atom is in fact a helium atom. Now, all atoms can be found in the periodic table. This shows all of the different atoms that there are. And we call different atoms elements. So for example, if I just circle one of these elements on the periodic table, here I've circled boron. So boron is an element. And basically, boron, the element, is made up of boron atoms. So an element can be defined as all the same type of atom. If I go over to the top right hand of my screen and I look at this box, you can see that I have an element over here. I can tell that it's an element because it is all the same type of atom. This could be hydrogen, which is known as a diatomic molecule. And that's another key word to learn, which is molecule. And this is called a molecule because of the fact it is bonded together. Anything that is bonded is called a molecule. So this picture is showing molecules of one element. In nature, however, we don't often find elements on their own. They often like to bond to other elements. And when this happens, we make what we call compound. And a compound is two or more elements chemically bonded together. If I look at this compound over here, I can see that I have two different types of element because of the fact they have different sizes. And depending on where the element is in the periodic table determines the atom's size. For example, the lower down in the periodic table, the bigger its atoms are. If I have a look at this bottom picture, you can see that I have a molecule of one element and I also have a compound here. Now these aren't bonded together, there's space between them. This means that I have a mixture. And mixtures are where you have two or more elements or compounds not bonded. There are many examples of mixtures in nature, for example, the air or the sea. And another key thing about mixtures is we can separate them. And that is what we're going to look at later in the video. What we're going to do now is just focus on compounds for a little bit because of the fact compounds occur in nature a lot because elements like to bond to other elements. So if I look at the first one here, I've got CH4. Now, every time I have a new capital letter, I have a new element. And if there is no number after that element, then it means that I only have one of it. So in this first one, CH4, I have one carbon and I have 4 hydrogens. So in total, I have 5 atoms and I have 2 elements. In terms of the name of this is in fact called methane. There are a few compounds which you just need to learn the names of, and methane is one of them compounds. The next one, I've got magnesium bonded to fluorine, and I can see that I have 2 elements present and I have 3 atoms because there's no number after my magnesium and there's 2 fluorines, so I have 3 atoms and I have again 2 elements. Now we're going to have a little bit of a look at a trick of naming these compounds, because of the fact when I have a metal bonded to one non-metal, it's always going to be the metal named first, magnesium, and then the second half of the name comes from the other element, so it's going to be magnesium, fluor, and then I change the ending from fluorine to fluoride. Now, if magnesium was bonded to oxygen, it would be magnesium oxide. Or if it was bonded to sulfur, it would be magnesium sulfide. If I have a look at the last example, I have 2 atoms of sodium, I have 1 of carbon, and I have 3 of oxygen. So in total, I have 6 atoms. Now, this time is a bit different. I have 3 elements. And in terms of writing its name, it's called sodium carbonate. And a little bit of a trick here is if it ends in an 8 at the end of the second element, then it's often containing oxygen as well. For example, sodium sulfate. Sulfate is SO4. There's a few negative ions that you do need to remember, and we'll go over those few in future videos. But for now, you just need to know that 8 means that it contains oxygen as well. Now we've had a look at naming some compounds, let's go back and look at atoms in a bit more detail. Now, atoms are actually made up of smaller particles that we call subatomic particles. And there are 3 subatomic particles that make up our atom. So if I focus here on the nucleus of the atom, which is my central part of my atom, my nucleus contains 2 subatomic particles. The blue ones here, the blue ones are named protons, and the orange ones here, which there are 4 of, are named neutrons. Around the outside of my nucleus in shells are electrons. And it's really important that you know some of these properties of these subatomic particles. So if I have a look at protons first, protons have a charge of +1, and the way I remember it is positive protons. The mass of a proton is also 1, and this is in atomic mass units, and the location, like I said earlier, is inside the nucleus. Then I have my neutron, and the way I remember its charge is neutral neutron. It also has a mass of 1 atomic mass unit, and it is located in the nucleus as well. Then around the outside in the shells we have electrons, which have a -1 charge and a mass, and this is quite a hard one to remember, of 1/2000, which is incredibly small. So sometimes they say that an electron's mass can almost be discarded from the actual mass of the atom because it's so tiny, but it does have a mass of 1/2000, and it resides inside shells. Now, just from looking at this atom, I could tell you what atom I actually have. And I can do that from the number of protons and neutrons that are present. So I could actually tell you, because it has 3 protons, that this atom is in fact lithium. And the reason is, if I look at lithium in the periodic table, it has the numbers 3 and 7. The atomic number here tells me how many protons I have. Now, atoms are always neutral. This means that the charges must add up to 0. So the atomic number, as well as telling me the amount of protons, also tells me the amount of electrons as well. So this means that lithium will definitely have 3 protons and also 3 electrons. Working out the number of neutrons is a little bit more tricky. We work that out using the atomic mass and the atomic number. The atomic mass tells me the mass of my atom. Now, the mass of our atom, like I said earlier, mainly comes from the protons and the neutrons because the electron's mass is so tiny. So to work out my number of neutrons, what I do is my atomic mass minus my atomic number. So for lithium, it will have 4 neutrons. Just simply 7 minus 3. If you can work out the number of subatomic particles in the atom, you can now go on and draw electron configurations. Now, the key thing to drawing these electron configurations is that atoms like to fill up their shells following something called a 2-8-8 rule. And what that means is in each shell, you can have a maximum of these numbers in each shell. So in my first shell, I can have 2. In my second shell, I can have 8. And in my third shell, I can have a maximum of 8 as well. So let's see what this actually means by looking at a few examples. Here I've got fluorine from my periodic table. And fluorine has an atomic number of 9 and an atomic mass of 19. This means that fluorine will have 9 protons, it will have 9 electrons, and if I work out the number of neutrons, that's the mass minus my atomic number, it will have 10 neutrons. So let's go ahead and look at how to draw my electron configuration for fluorine. So in my first shell, I'm allowed a maximum of 2 electrons. So let's draw them in. When we represent our electrons with crosses, you need to be really careful with drawing these electrons to make sure they are touching the shell as well. And so far I've drawn 2 electrons out of my 9. This means that I have 7 left. And the way I always draw it is I always fill out north, east, south, and west. So let's have a look at my next ones. 1, 2, 3, 4. So far now I've drawn 2, 6. I've still got 3 more to go. And now I can start pairing up my electrons. 1, 2, 3. That is an atom of fluorine. Let's just do one more example together. Here I've got boron, and if I look in the periodic table, it has an atomic number of 5 and an atomic mass of 11. This means that boron will have 5 protons, it will have 5 electrons, and to work out the neutrons, remember, you do the atomic mass minus the atomic number, so it will have 6 neutrons. Let's try and draw them electrons in then. So in that first shell, I'm allowed to have 2 electrons. 1, 2. In my second shell, I'm allowed a maximum of 8, but I won't need all of them because I've only got 5 electrons in boron. So I've already drawn 2, so I've got 3 more to go. Remember, north, east, south. There we go. That is my atom of boron drawn as well. Now, atoms rarely like existing in their pure form, mainly because of the fact that they like bonding to things and they want to actually have a full outer shell. And one way that an atom can gain a full outer shell is by losing or gaining electrons. Now, when atoms do this, they are no longer neutral and they become what is called ions. Now, if I have a look at some electron configurations, I can show how different atoms can become ions. Now, metals, what they do to become ions is they lose electrons. Now, earlier we looked at boron, and boron has the atomic number of 5 and the atomic mass of 11. This means that the atom of boron is going to have 5 electrons. So let's draw them in. Remember, 2 can go in the first shell, and then 3 will be in my next shell because of the fact it only has 5 electrons. Now, this is my atom. This will be neutrally charged. It will have 5 protons and 5 electrons. But let's have a look at what happens when it becomes an ion. Well, to become an ion, boron is going to want to lose 3 of its electrons, so it has a full outer shell. This means that it will only now have 2 electrons. Now, because it's lost 3 electrons, we'll put a bracket around it and we put a 3 plus in the top right-hand corner. The way I like to remember which charge is positive or negative is I think of electrons like naughty children in my classroom. And if I've lost 3 naughty children in my classroom, I'm very happy. So that is why I have my 3 plus. Let's have a look for a non-metal now, and let's have a look at oxygen. So if I find oxygen in the periodic tables, it has the numbers 8 for atomic number and 16 for atomic mass. So this means that it will have 8 electrons in total, and in its outer shell it will have 6. Now, as you can probably see, oxygen needs to gain 2 electrons in order to have a full outer shell. So let's see what that looks like down here. And there I've drawn my electrons in, and because it's gained 2 electrons, it will have the charges 2 minus. Now, the reason for this charge is because of the fact that the difference between the number of protons and the number of electrons, and it will have 8 protons in its nucleus, and it now has 10 electrons. Now it's an oxide ion, and if you do 8 minus 10, you end up with -2, which is its charge. Now, if you have a look at the periodic table, there is a few elements that you see on it which has an atomic mass that has a 0.5. For example, if I look at chlorine, chlorine has the atomic number of 17 and it has an atomic mass of 35.5. Now, this means that I can still work out my number of protons and my number of electrons quite easily. It's going to have 17 protons and 17 electrons, but my number of neutrons is harder to work out because of the fact it's got a 0.5, and we can't have 0.5 of a neutron. So what actually is going on here? Well, what goes on with chlorine is the fact that it has 2 isotopes. There is chlorine 35 and there is also chlorine 37. So what actually is an isotope? It is an atom that has the same atomic number but a different atomic mass. So if I focus on these 2 atoms that chlorine has, chlorine in its 35 atomic mass state will have 17 protons, 17 electrons, and if I do 35 minus 17, that gives me an answer of 18 neutrons. And if I look at my chlorine 37, it will have 17 protons, 17 electrons, and now it will have 20 neutrons. Now, let's go back to this term that we looked at earlier, this relative atomic mass, and this number here. So how do they know it's 35.5 for chlorine? Well, if I was to give you a sample of chlorine, then what it would contain is 75% of chlorine 35 and 25% of this isotope chlorine 37. So if I was to work out the relative atomic mass of chlorine, what you need to do is use this equation up here, the mass of isotope A times its abundance plus the mass of isotope B times its abundance divided by 100. If there are more isotopes, you just keep doing the same. So the relative atomic mass of chlorine will equal 35 times by 75 plus 37 times by 25 over 100, and that is where I got that 35.5 from. Now, what we have to do now is have a little bit of a history lesson. And the reason why we have to have a bit of a history lesson is because of the fact the model of the atom has changed over time. So it didn't always look as what it does now in your science lessons. So let's have a look at what discoveries led us to improve on what models we have. So the first model we're going to look at is by John Dalton. And John Dalton basically came up with the theory that everything is made of atoms. And all he did to represent atoms was draw a small sphere. He also said that different elements have different atoms as well. The next discovery was from a scientist called J.J. Thomson, and he discovered the electron. And the model he created is called the plum pudding model. And the reason why it's called the plum pudding model is because the electrons that he discovered were distributed inside a sphere of positive charge, and it looks a little bit like a plum pudding. The next model is starting to look like the design of the atom that we know today, and the reason is because of the fact this scientist discovered the nucleus, and this scientist has the name Rutherford. And the way he discovered the nucleus was he did an experiment called the gold foil experiment. Another name for the gold foil experiment that you might have heard of is the Geiger-Marsden experiment, and sometimes examiners flip between the two. Now, in this gold foil experiment, what Rutherford did is he fired positive particles at a thin sheet of gold foil. These positive particles are called alpha particles, and what he did was he fired them at this thin sheet of gold foil. Now, what would have happened if J.J. Thomson's plum pudding model was correct is that all of these alpha particles would just pass straight through the gold foil and be detected. However, this was not observed. What he in fact noticed was that most of them did go through. About 99% went straight through. And this proved that the nucleus is incredibly small. But what happened with a really tiny percent is that a few of them hit the nucleus and bounced back. Now, what this proved is the nucleus is incredibly tiny and dense. This is where most of the atom's mass must be. Then a few also swerved as they passed the positive nucleus. And this led to the conclusion that my nucleus is positive. So the three conclusions from the gold foil experiment is that the nucleus is tiny, that the nucleus is positive, and that the nucleus is dense. The next scientist we're going to look at is Niels Bohr, and what Bohr discovered was the 288 rule. He found out that electrons reside in shells, and there can be 2 in the first shell, 8 in the second, and 8 in that third shell. And then the final discovery was by James Chadwick, and Chadwick discovered the neutron. And there's a reason why the neutron was discovered last, and this is because of the fact it's neutral. This makes it hard to be discovered, as if you fire an alpha particle or another charged particle at it, the neutron will have no real influence on what that particle does. You will be very pleased to know that we are finished looking at atoms for the time being, and we're going to focus on mixtures now, and specifically we're going to focus on how to separate mixtures into their different components. And the first method we are going to look at is chromatography, which you have probably done in year 7 and year 8 as well, so you will definitely have a basic understanding of what it is before going into doing your GCSEs. Chromatography actually separates mixtures based on their solubility. And what we do to run a chromatography is we have our chromatography paper, which is called our stationary phase. And what we do with our chromatography paper is we draw a baseline in pencil. And the reason why we draw our baseline in pencil is because we know that pencil is insoluble, so it will not travel up my chromatography paper when I introduce my mobile phase, which is what the solvent is, which will travel up your chromatography paper, separating your mixtures into its components. Now, once you've got your chromatography paper and you've drawn your baseline, what you're going to do is you're going to put your different samples on that baseline. So here you can see that I've put 4 different samples on my baseline. I've put A, B, C, and U. U is an unknown and something that we need to work out what actually is in it. So if I have a look at my chromatography, I can see that A, the mixture A, is made up of 2 components. B is made up of 1 component. We can actually say that B is pure because it is only made up of 1 component. C is also made up of 2 components, and U is made up of 3 components. So if I was to analyze this chromatography and you were to ask me what the unknown is actually made up of, well, let's have a look at the different spots. Here you can see the unknown has 3 in total, here, here, and here. And if I go across from each spot, I'll find that there's 1 from A here and also from B here. So that means my unknown is made up of A mixed together with B. Now you can quantitatively analyze a chromatography as well. That just basically means you can use numbers to explain a chromatography as well, but you won't need to look at that until we do chemical analysis later on for paper 2. Another way to separate a mixture is using a technique called distillation. And distillation separates a mixture based on their boiling point. So let's have a look at how distillation works, and it's basically 3 main principles. The first being heat, and you can here see that I am heating using a Bunsen burner. The second stage of my distillation is evaporate, and you can see that I'm evaporating here using my round bottom flask. Now, if I have a look at my mixture down here, it could be ink and water, for example, as they have different boiling points. What's going to happen when I heat up my mixture containing ink and water that's in the round bottom flask is my water has a lower boiling point. This means that it's going to evaporate, leaving the ink behind. Now, this takes me on to the next piece of my apparatus, which here is my condenser. And what happens in my condenser is it will turn the water back from being in its gas phase to liquid. So that's my next stage of my distillation: heat, evaporate, condense. And then finally, my water will be collected here. And this is in a conical flask. Now, another key thing about the condenser is that you put the water in from the bottom. So water goes in here and water comes out here. Now, there's a reason for that, is because you want your water to stay cool for as long as possible. So by putting it in here and getting it out here, the water will not heat up in the condenser, and this means that it will stay cool enough to condense the water, the pure water that you want to collect. Next method of separation we are going to look at is separating soluble and insoluble solids. So if I look at rock salt, salt is soluble, meaning that I can dissolve it in water, whereas the other rocks that are present in rock salt are not soluble. So the first step that I do in separating rock salt is add water and stir. What this will do is it will make the salt dissolve into your water. The second stage will be to filter. The filter will remove all of your insoluble solids and you can then throw them away. After filtering, I will be left with a mixture in my evaporating basin that only contains salt water. And in here, in my evaporating basin, I only have salt water, and all I'm going to do is heat it up. And I'm going to heat using a Bunsen burner and a tripod, which will have my evaporating basin on top, and I'm going to heat and evaporate half the water away. And then my final step is collecting my salt crystals and drying on a windowsill. So all I do now is place my remaining salt water. There should be about half of the water left, and you're going to put it on a windowsill and you will collect your pure dry salt. Now we're going to go into a bit more detail on the periodic table and look at how the elements are ordered, and also have a look at some key areas inside this table. Now, first thing to say about the periodic table is you are given this in your exam. In even little end of unit tests, I'm sure your teacher will provide you with one of these. But you need to know some key things about the table, not necessarily remember all the elements and where they are positioned. So the first thing to say about this periodic table is that the elements are arranged in what's called groups and periods. Now, groups are the vertical columns going down. So I have group 1 here, group 2 here, group 3 here, 4, 5, 6, 7, and then this last group is either called group 8 or group 0. It doesn't really matter which one you say. Then periods are labelled going across, the rows going across. So I have period 1, which only contains hydrogen and helium, period 2, which starts off with lithium, period 3, period 4, 5, 6, 7. Now, the reason that the periodic table is arranged in groups is the fact that elements in the same group have similar properties. For example, all elements in group 1, which is known as the alkali metals, are incredibly reactive. Group 2's name is the alkaline earth metals. I'm just going to go through some key names that you need to know for some of these groups. You don't need to know the names of all of the groups, just some of the key ones. Then you need to know group 7, which has the names the halogens, and group 8 or 0, which are the noble gases. Now, another thing that you could do with the periodic table is you can divide it into metals and non-metals, as I have done with the black line here. The elements to the left-hand side are the metals. There is a lot more metals in the periodic table than non-metals. So all of these elements on this side of the periodic table are metals, and all the elements on this side of the periodic table are non-metals. The elements that I've highlighted in yellow are called metalloids because they can exhibit properties of metals and non-metals, but you don't need to know much about them. You may also know that I've left a large section in the center which doesn't have a group, and the reason for this is these are called the transition metals here. We'll go into more depth about each of the key groups and the transition metals in a bit later in the video, but let's first have a look at some of the differences between metals and non-metals. So there are many physical properties that will help you identify whether you've got something that is metallic or non-metallic. For example, metals are often shiny. They are malleable, which means you can change their shape without them breaking. They also often can be sonorous, meaning when you hit them, they make a sound. And as well as this, they have high melting and boiling points. And this usually means that they are a solid at room temperature. So if we look at non-metals, they're basically the opposite of metals in the fact that they are usually dull, brittle, which means if pressure is applied, they usually break up into many pieces. They're often found in a lot of different states at room temperature, and they often have low melting points and boiling points. If we look at some of the chemical properties as well, metals, remember when we looked at ions earlier, they always lose electrons, and non-metals will always gain electrons to get a full outer shell. But in addition to this, non-metals can do a special type of bonding called covalent bonding, which metals are not capable of. This is where electrons are shared, but we'll go into covalent bonding in a later unit. Just like with the model of the atom that we looked at earlier, the periodic table has not always looked as it looks now in the modern form, as we've discovered more elements and we now know how to order them in its table. The first model of the periodic table was actually come up with by a scientist by the name of John Newland, and his table is called Newland's octaves. And what he did was he arranged the periodic table in increasing atomic mass. And when he started to arrange them in terms of the atomic mass, what he noticed was that every few elements, they started to react similarly. So he arranged them in groups according to this. So as you can probably see, you might notice some from the earlier periodic table. Here, for example, are my alkali metals, and I've got fluorine, chlorine, and bromine and iodine, the halogens, in the same group. However, this model of the periodic table is not perfect, and you might see places where some elements look very out of place, and there's a few reasons for this, as we'll go on to a little bit later, but let's have a look and see if we can spot some of the mistakes that Newland made in creating this table. Well, if we just have a look just here, he's put copper in with lithium, sodium, and potassium. Now, alkali metals are incredibly reactive, as I said earlier, whereas copper is an unreactive metal. So what he's done is he made a mistake in the fact that there's some elements that do not fit the pattern in certain groups. Also, what you might have noticed is here, if I look at cobalt and nickel just here, he's put two elements in the same box. And if I still focus on this cobalt and nickel in the same group as the halogens, well, this means that he has mixed metals and non-metals in the same group. So this was a good first model of the periodic table, as he started to realize that there was a pattern in the elements, and it just needed taking a step further. And the scientist who did that was Dmitry Mendeleev. a Russian chemist. And what Mendeleev did is he took this idea of Newland's octaves and improved on it. He realized that there was a pattern in the elements and the properties were repeating. However, he realized that there must be some undiscovered elements, and this is the key bit. He found out that there must be undiscovered elements, and what he did was then he left gaps in the periodic table for these elements to be discovered. And you might say, well, why did scientists believe Dmitry Mendeleev's periodic table to be correct? Well, what Mendeleev did was he realized that there must be these undiscovered elements. And then when these elements were discovered, he knew exactly the properties that they should have. For example, francium that doesn't show up on this periodic table, he knew that because it was an alkali metal and in group 1, it would be an incredibly reactive metal, and that would be the group that it should go in because it matches the pattern of that group. In addition to this, the elements are now no longer arranged just in atomic mass, they are arranged in atomic number. But obviously, when these scientists were around, they had no knowledge of the subatomic particles, and therefore they couldn't arrange the atoms in terms of atomic number, only atomic mass. What we're now going to do is focus in on some of them key groups in the periodic table that you need to know about. So the alkali metals, the halogens, the noble gases, and have a little bit of a look at the transition metals as well. So the alkali metals are found in group 1 of the periodic table. This means that all of the alkali metals have 1 electron in their outer shell. And because they only have 1 electron in their outer shell, these alkali metals are very reactive. This is because of the fact it's very easy to lose 1 electron. If you've got more electrons, it gets a bit more difficult to lose more. As well as being incredibly reactive, they are also soft, meaning that you can cut them with a sharp knife. And just like all metals, they are shiny. Now, what you've probably all seen is your teacher add alkali metals to water. And when this happens, what happens is the alkali metal reacts with the water and it makes hydrogen gas. This is why going down the group, sometimes you actually see sparks because hydrogen is incredibly flammable, and it also makes an alkali, a metal hydroxide. Now, what should have been observed when your teachers added these alkali metals to water is that lithium is the least reactive, and you should maybe only observed some light fizzing when this happens. When you added sodium, it should have fizzed a bit more vigorously than it did with lithium. Potassium, you should have seen a beautiful lilac flame. And then your teachers might have shown you rubidium and cesium. You start to get small explosions happening with this. So the first trend you need to know is that it gets more reactive down the group. As well as the reactivity increasing down the group, also density has the same pattern. They get more dense going down. Now, if they didn't react so quickly, what you'd actually see is potassium, rubidium, and cesium would in fact sink. They have a higher density than water. The only thing that increases up the group is melting point and boiling point. You might have noticed when your teacher showed you a video that cesium is almost in a liquid form when you see it in that little vial. The next group we are going to focus in on is the halogens, which is group 7 of the periodic table, meaning that they all have 7 electrons in the outer shell. The halogens are characterized by being incredibly toxic. And you might know that chlorine's used in swimming pools because of the fact that it can destroy a lot of the bad bacteria that can build up in your pool. In terms of the reactivities, they are reactive and they especially like to react with group 1. So they like reacting with the alkali metals. And the reason for this is that the halogens only have to gain 1 electron and the alkali metals like to lose 1 electron, so they like reacting together. Okay, so let's have a look at some of the properties of these different halogens that we have in the group. So if I start off with fluorine, fluorine is a yellow gas at room temperature. Chlorine is also a gas, but this time it is a green gas. Bromine is in fact a brown liquid. Iodine is a dark brown solid. Astatine is a black solid. So probably, as you've noticed, you see that as you go down the group, the melting point and the boiling point increase. The opposite is observed with reactivity in group 7 though. As you go up the group, they get more reactive. So this means that fluorine is the most reactive halogen. Don't worry, we will explain why the alkalis and halogens reactivity does change up and down the group, but that just is a little bit later on in the video. The last key group that you need to know about is the noble gases. And the noble gases are really characterized by the fact that they are incredibly unreactive. This is why they were the last elements to be discovered in the periodic table, is because it's quite hard to find things that are so unreactive. The reason why they are unreactive is because they all have full outer shells. This means that they don't really want to react with anything else because they already have a full outer shell. Because of the fact they are so unreactive, they have quite a lot of uses where you need something that is inert. They're often called inert when they don't react with something else. For example, if you wanted to store something that is highly reactive, think of them alkali metals down the lower end of the periodic table. You might want to store them under helium or argon because of the fact they are so unreactive that they will not react with that substance. Something you also might know already is that the alkali metals get more dense going down the periodic table. The reason why you might already know this is because you know that when you put helium inside a balloon, that balloon will inflate. Whereas radon or xenon, if you were to put them inside a balloon, they would in fact sink the balloon. Now, all of the noble gases are gases at room temperature. However, the melting point and boiling point increases down the group, just like with the halogens. We're now going to focus on that block in the center of the periodic table called the transition metals. And the reason why the transition metals are not put in any group is because of the fact they have what's called varying oxidation states. And this means they can form ions where they've lost more electrons. As well as having various oxidation states, they also form colored compounds. And they are incredibly useful as catalysts, things that speed up reactions without being changed themselves. Because of their coloured compounds, they are also found in many dyes and even, in fact, in jewellery. If you were to compare the transition metals to the alkali metals that we've already talked about, what you'd notice is the transition metals are not that reactive really. They're also much stronger and denser, and they also have a very, very high melting and boiling point. We're now going to look at a property called shielding, which causes the changes in reactivity going down group 1 and group 7. So firstly, let's just draw the electron configurations for a couple of the group 1 alkali metals. So if I just draw it for lithium here, it only has 3 electrons. And if I draw it for sodium as well, I just have exactly the same 1 electron in the outer shell, but this time I have a extra shell as it's further down. It's got one period down in the periodic table. Now, when lithium and sodium are reacting, what they are doing is they are losing an electron to get a full outer shell. So if I have a look at what that means for lithium, all it means is it's going to lose 1 electron and it's going to become a 1+ ion. And the same thing will be observed for sodium, but this time the electron is further away from my nucleus. Let's have a look. So it now becomes a 1+ ion, but it still has that extra shell there. Now, the reason that sodium is more reactive than lithium is to do with the position of this electron from the nucleus here. Now, if you remember back to the start of the video when we were talking about protons and electrons, you'll remember that protons are positive and protons are found in the nucleus, the central bit of the atom. And what happens is the electrons are attracted to those protons in the center of the atom because they're oppositely charged. Electrons, remember, have a -1 charge, protons a +1 charge. Now with the lithium atom here, you'll notice that the electron is very close to the nucleus. There's only 1 shell guarding it. This means that the electron is much harder to lose. The positive protons, the attraction from the nucleus, is going to keep hold of that electron much more. If we look at sodium here, it's easier to lose this electron because of the fact it's further from the positive nucleus, so it's feeling less nuclear attraction. That's what we call it, less nuclear attraction. That's the attraction from the positive protons in the nucleus. And we call this shielding. The nuclear attraction has been shielded, so there is more shielding in sodium than there is in lithium. If we have a look at group 7 now, and I look at fluorine and then compare it with chlorine, I'll just draw fluorine first. It has 7 electrons in its outer shell, just like that. And if I have a look at chlorine, it's exactly the same, just that there is 1 more shell of electrons because it is a period lower on the periodic table. So let's get them electrons drawn in. Well, what's going to happen when these two react is they're going to want to both gain an electron. So let's have a look at what happens with that then. So if I put the electrons in onto my 2 atoms to make ions, so here I've drawn fluoride, I've drawn fluoride down here, and because it's gained an electron, it now has a -1 charge, and the same thing will happen with chlorine over here to become chloride. It's going to gain an electron, and when that happens, it's also going to be a -1 charge. So I draw my brackets around it, and I put my -1 in the top right-hand corner. Now, it's basically the same theory as before. This time, though, the fluorine, instead of trying to lose an electron, is obviously trying to gain an electron. Now, it's easier to gain if you feel a greater positive charge. So there is less shielding in fluorine than chlorine. This means that there is a greater nuclear attraction, and this means it's easier for fluorine to gain an electron. And for this reason, you get in group 1, the reactivity increases down the group, and for group 7, the reactivity increases up the group. Because of the changes in reactivity going down group 7, what you can do is you can carry out what's called displacement reactions, in which a more reactive halogen will displace a less reactive halogen from its compound. So here I've got potassium chloride, so the potassium's happily bonded with chlorine, and fluorine has come along and it stole the potassium away. The reason for this is because of the fact fluorine is more reactive, so it has displaced the chlorine from its compound. The way I sometimes teach it to my class is that I say that fluorine is kind of like a bombshell in Love Island coming in, and because it's more reactive, it's going to steal the potassium away. Now, it might ask you what you could observe in a reaction like this as well, and you've got to just remember the colours of the different halogens. So, for example, fluorine is a pale yellow, and if you've got chlorine, what you should see is the solution maybe go a green colour. And if you'd formed bromine, you'd just have to remember that you'd make an orange-brown solution. And that is all for today's video. I hope you've enjoyed it. Remember, if you have enjoyed it, please drop it a like and subscribe to the channel. Let's have a look for a non-metal now, and let's have a look at oxygen. So if I find oxygen in the periodic tables, it has the numbers 8 for atomic number and 16 for atomic mass. So this means that it will have 8 electrons in total, and in its outer shell it will have 6. Now, as you can probably see, oxygen needs to gain 2 electrons in order to have a full outer shell. So let's see what that looks like down here. And there I've drawn my electrons in, and because it's gained 2 electrons, it will have the charges 2 minus. Now, the reason for this charge is because of the fact that the difference between the number of protons and the number of electrons, and it will have 8 protons in its nucleus, and it now has 10 electrons. Now it's an oxide ion, and if you do 8 minus 10, you end up with -2, which is its charge.